So about that cloud computing, few things I think you need to know. When it comes to cloud computing, you need to be able to recognize SaaS, S-A-A-S, PaaS, I guess you say it like that, P-A-A-S, and I can't pronounce the other one because there's no pronunciation, but IaaS. So that's software as a service, platform as a service, and infrastructure as a service. Be familiar with those. Now that software as a service, you're using the applications as the end user, right? Like an operating system and applications, they're already installed. You don't have to worry about that. You get software as a service and they're taking care of everything. They're taking care of the server, they're taking care of the patches, they're taking care of the updates. Nothing is on you. You're just using their services. Software as a service, like webmail, Office 365, Google Plus, right? All of that is software as a service out there ready to go. You don't have to worry about the back end. You're just paying for an application. Now, if you want a little more control, you could get a platform as a service. Now, these are configured services. So now the operating system may be there and you don't have to worry about that. But if you need a particular platform, you may have to worry about that. Like, could be web hosting. Software developers use platforms as a service sometimes because they'll get the server, the cloud-based services, and they'll put whatever development they need up there and use the power of the cloud to make it happen. And you can have infrastructure as a service, the IaaS. And this one gives you, I don't want to say total control, but it gives you a lot of control over your own server now because it is a virtualized operating system. It is like a VM on your host computer. We've talked about virtualization a little bit, and if you had a desktop or server system, and that's your host computer, and we loaded some type of hypervisor on there, VMware, Hyper-V, whatever you prefer, we can put guest operating systems on top of that. Now, if you weren't the only server admin and you gave people permissions to use those VMs, they would be responsible for those, right? They would be responsible for operating system installs, operating system updates and patches, application installs and patches, firewall settings for that particular server, any access control. That is like their server. Nobody else has control over that except the underlying system admin. Now take that and stick it out in the cloud somewhere. So we still have a service or system admin somewhere, and they are a dime a dozen, by the way. You can look that up online and find all kind of virtual operating systems, or they call them virtual private servers, VPSs. So you could do a search for a VPS, and there's tons of them out there. And you buy a VPS. You're leasing, renting a server monthly. And depending on what you need 2 gigs of RAM, so many cores, so much hard drive space, and they'll have limitations on your bandwidth as well, probably. The more you pay, the better server you get. And these are virtual servers sitting somewhere out in the cloud, and you are solely responsible for it. Operating system installs, sometimes they give you the operating system for it because they've already licensed it, which is a good thing for you because now you don't have to go pay for a license. But big but there, you do have to patch it. You have to update it. You have to put your antivirus, anti-malware. It's like a physical computer sitting at your house, except it's all cloud-based. So that is infrastructure as a service. So know those three: software as a service, platform as a service, and infrastructure as a service. And then we have those distributed systems. Now we're talking about grid computing. Still a type of distributed systems, but grid computing represents a distributed computing approach that attempts to achieve high computational performance by different means, non-traditional means. So it attempts to harness the computational resources of a large number of dissimilar devices. So it's trying to take the processing power of anywhere that it can, not necessarily a server or a laptop, but maybe a gaming console, right? We can take those, you hear about grid computing, popular gaming consoles where they can tie them together and make a little computer. They can rebuild them. So that could be a form of distributed system. We also have peer-to-peer networks. And we're going to mention this a couple times, but they kind of alter the whole client-server thing. In the name should give it away because it's peer-to-peer. Peers are your equals, or so they say, right? Peers are your equals, so nobody's really in charge. So any system in a peer-to-peer network may act as a client, it may act as a server, it may act as both. Because if I'm talking to you and you're giving me resources, you're the server, I'm the client now. But then on the other end, I'm giving somebody else resources. So now I'm a server and they're the client. But I'm still getting things from you, so see how I can be both or either or? It depends on the data needs, depends on how you have it set up. Now, peer-to-peer networks, they are decentralized. When they're decentralized, they're a little more resilient, all right? There's no central servers that we can take down. It's like a client-server relationship. If we have a bunch of clients tied to a server and somebody takes that server down by whatever means, none of the clients can be serviced anymore. So your whole network is down. But in a peer-to-peer, right, we're all just kind of tied together somehow. You may have all these connections, logical connections to other individuals. And if that one device or one node goes down on your peer-to-peer network, oh well, I'm not going to be able to get any data from them, but it doesn't take down the whole network. I can still get here and here and here and here and here. And if that goes down, I don't care. I can still get here, 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 and here. I just can't get that data, obviously, and I won't be able to get their data. So that could be a distributed system where we pass everything around. Now, this is not necessarily ideal for enterprise settings, especially if you're going to set up a true peer-to-peer network. I'm not talking about using applications like torrents or something like that for peer-to-peer. I'm talking about my computer is plugged in to their computer somehow, to their computer, to their computer. It could work in a small office, 3 or 4 computers, but if somebody needs to access something on my system, they need permissions. I'll have to give them an account, or we'll have to use a shared account. I know, I said it out loud, right? We don't want to use shared accounts, no accountability, but we would have to give them an account. So they would have to have one, they would have to have one, they would have to have one, and vice versa. So 2 or 3 computers, not a big deal. Hundreds or thousands of computers, that's some job security for you, but it's going to be an administrative nightmare. So that's why we use the client-server scenario when it comes to the type of enterprise setup. And then a little bit about the cryptographic systems. There's 3 primary types that we need to be familiar with: symmetric, asymmetric, and some hashing. Now, symmetric encryption uses one key. The same key is used to encrypt the data that is used to decrypt the data. We use this a lot in wireless technologies. And I don't want to steal the thunder. We're going to talk about cryptography a little bit later, so maybe a little vague right this second. Asymmetric cryptography, asymmetric, uses 2 keys. So we encrypt with one key, and we have to have the other key, because it has a relationship with it, is needed to decrypt that data. And then hashing is a one-way cryptographic transformation using whatever algorithm. There's a couple in there we're going to talk about, but we use hashing for integrity. So we can see the digital fingerprint, if you will, of that file or that folder or that whole hard drive for that matter. So those are those cryptographic systems that we need to file those away, but we can use these, and we do use these all the time. Then a little bit about the industrial control systems. Specifically, I want to mention SCADA, Supervisory Control and Data Acquisition Systems. These are an assembly of interconnected devices and equipment, and it's used to monitor and control physical equipment, say in industrial environments or in power plants, nuclear facilities, water treatment plants. You could have smaller versions of this in, say, college campuses. We had one at an old job where they controlled the HVAC system with a centralized system. This would be a centralized system. You know, you've seen the movies, the TV shows where there's a couple guys, a couple employees in a control room, and it has access control. Usually they have to have special badges to get in there or know the key code or whatever. But they go in what they call the control room, and they can control maybe the whole plant by this one room, because everything comes to that one area. Because if I flip a switch here, it runs to a little device, maybe like a PLC controller, that will open a valve or close a valve or whatever, speed something up or slow something down. There are some threats against these, though, that we need to be familiar with when it comes to industrial control systems, because we've heard the threats and the threats and the threats about these for a long time now, and they're real threats. Could come under a DOS or a DDoS attack, a denial of service attack. If I can somehow present a DOS attack to that control system, you can no longer control what's going on. If something starts to overheat or it's not acting properly, it causes problems inside of your industrial complex there. Well, that's going to be a real problem, right? Because you can't control the motors, you can't control valves, you can't control anything if I DOS you, because I'm taking that availability away. Could have unauthorized access if somebody could get in the control room. And sometimes, nowadays, you know, we see this big board, but now we're porting that stuff to traditional computers. Right? That is a big computer out there, right? You have little gauges everywhere and buttons and knobs and everything. But if you can take that information and port it to, say, a regular system, and now we can just point and click, well, that's a little more susceptible because we have exploits already for computer systems. So that could be unauthorized access as well. If somebody remotes into your computer unauthorized, if they hack you, if you bring in a virus or Trojan, some way I can communicate with it outside of the system, or physical access. Right? If I get into the control room or that secured room or restricted area, I may be able to have unauthorized access. May have just human errors. Right? We make mistakes. Everybody makes mistakes every once in a while. As much as we want to think we don't when it comes to IT, we do. We make mistakes all the time. And there could be human errors in industrial control systems. He thought he turned it to the right, and he turned it a little too far. Or she was supposed to turn that off, and they forgot. Spilt something on there. Shorted out the board, or something like that. Human errors. They happen. Could have attacks on end system or the office networks. So we know we're not successful getting to the control room or the control board. They got access controls in place. But what if I compromise one of the other computers inside of the infrastructure? Does it have a logical path to get to that system that I want? It may take me a while, but I may be able to get there using the office network or some type of other end user system. Or that unauthorized remote access that I talked about just a second ago. Maybe you remote in and you're not supposed to. That's against company policy. You know, you didn't want to leave your desk, or for whatever reason, you know, you were playing in the company softball game the other day and you hurt your leg. So you can't You don't want to hobble in there to the control room. I'll just remote in this one time. It'll be okay. I'll just telnet on over. Well, right, you just telnetted on over in plain text. You got caught in the man-in-the-middle attack. Somebody has stolen your credentials now. And in a couple weeks, we start seeing things going wrong because of unauthorized remote access. We also have some vulnerabilities in our web-based systems. So let's talk about XML, Extensible Markup Language. Now, this language is designed as a standard. This is a standard way to encode documents and a standard way to encode our data. And it is a standard out there on the web. It's international. It's kind of like HTML, but it's a little more universal than HTML is. It's used on the web, but it's not tied to it. You can have XML files for your operating systems because it could be like a data repository. HTML is a scripting language. It says this is the way to make this look. XML says this is how it looks, but it can hold information in there as well. You can even make your own data formats when it comes to XML. That's the extensible part. HTML has rules. XML, they have frameworks, but you can put things in there. You can make up your own as long as they match up. We can use this to store application configuration, like I was talking about for operating systems or applications that you may download or buy. We could have output from auditing tools put into XML files. So you can take that XML file and send it off to the vendor, and they can read it and understand the error messages that you are receiving on that operating system or that particular application. And there's tons of uses for XML, but I just wanted you to be familiar with it, and we're going to talk about it again a little later. And then another one we need to talk about is SAML, S-A-M-L, Security Assertion Markup Language. When you hear that, you're probably going to think single sign-on, and that's a good idea because this is an XML-based framework. So this came from how we developed XML for exchanging security information. So it also has authentication data in there as well. So one goal of SAML, like I said, is to enable web single sign-on at an internet scale. So you're not necessarily in your infrastructure and you're not bouncing from your organization's application to application. Now we're talking about web-based stuff. And if you think about it, they're going to start integrating this with cloud computing because everything is moving up to the cloud. Everything's going to be on virtual machines out there in the cloud pretty soon. Another one for web-based systems is Java. This is an object-oriented language. All right, another, we haven't talked about, but this is a programming language. It's used not only to write applets, because you can write Java applets, but as a general purpose programming language. Now, Java bytecode is platform independent, which makes it extremely flexible and extremely popular. It's interpreted by a Java virtual machine. So you write code in Java, and this Java virtual machine is what interprets that code to give you the output or to make it do whatever it is it needs to do. Now, Java is all over the place because it's platform independent. It may be in your mobile devices. It may be in your vehicles. It may be on airplanes. It may be hundreds of places. I think if you go download it, they say they're in thousands of devices, and it's true. It could be as little as in a digital watch, right? They can have Java everywhere. It's on your computer, maybe. It's on laptops. Some games run off of Java, right? Your phone can run Java. So it is platform independent. Now, the security side of it. This is ran in a sandbox. It's a good thing because this segregates the code from the operating system. That's the idea. Now, the sandbox is designed to prevent an attacker who is able to compromise the Java applet from accessing, say, the system files, like your password files or your DLL files or any critical files to make the operating system run smoothly. Now, we also have something called ActiveX. and this is a Microsoft thing. This is not platform independent. These controls are the functional equivalent to Java applets. They use digital certificates, though, instead of a sandbox to provide security. Now, unlike Java, ActiveX is a Microsoft technology, like I said, that works on Windows operating systems only. So you can have these in your Windows operating systems. You may see this in Internet Explorer. You may see it, well, you can download ActiveX to anything, but where ActiveX gets a bad rap is that it can actually talk to the operating system. So you could have your web application craft an ActiveX control that talks directly to the operating system. If it's an untrusted ActiveX control, that may be a problem for you, because now you're allowing somebody to talk to your operating system with whatever type of rights, and that could be unauthorized use, could be against policy. So that's one route. We got to be careful with ActiveX controls. You might want to turn that one off automatically. And I don't need Microsoft emailing me. I'm not saying it's all bad, but they do have some vulnerabilities built in there. So we have to, have our due diligence and make sure that we're doing it the right way. And then more about our web-based is the OWASP folks, Open Web Application Security Project. And if you've got time, once you get done with this video series, right, you might want to go check these guys out. Do a search on the web for them, OWASP. I think it's a .org out there. But they have lots of good information about web development and web application development. They probably one of the best security resources out there on the web. They provide a tremendous amount of free resources dedicated to improving application security posture. They have videos on YouTube. They've got training videos for development on their website. And they've got documentation upon documentation on secure coding practices, on what to do, on what not to do. For, say, example, SQL injections, cross-site scripting, cross-site request forgery. These guys help us out with that. Now, one of their best projects that they have, they call it a project, is their OWASP Top 10 list. And it's their Top 10 project is the way they call it. But they list out what are considered the most 10 dangerous application security risks that we have out there. So they will list them out, like malware. SQL injection has been number one for a long time now. I say a long time. I think the last one I saw was the 2013 report, I think is the last one they've put out. SQL injection was at the top of that list, I believe. It was on there the iteration before. And it's a collection from industry standards and professionals in the industry. It's not like OWASP says, well, I think it's SQL this year, or, well, they gave us the most money, so let's put them out. It's not like that. They look for trends. They do the research. They don't put it out like every 6 months. They do a lot of research. They get a lot of feedback from the professional community, and that's how that list is generated. That's why they call it a project and not just their top 10 list for the week or anything like that. Now, we do have vulnerabilities and defense in mobile systems. So defenses include policy administrative controls, like restricting the use of mobile devices through this policy. Have a policy in place in the first place saying you can't have mobile devices, because they are very good avenues anymore to bringing vulnerabilities into your organization, to bring in vulnerabilities into your infrastructure. So we might have technical controls. These are put in place to mitigate infective mobile computers, including requiring authentication at layer 2 of the OSI model using 802.1x. Now that could be bundled with additional security functionalities as well, like verification of current patches and antivirus signatures. What did I say earlier? That NAC, right? The Network Access Control, or NAP, Network Access Protection. where we look at those signatures and say, well, do you have the latest ones? Yes. Do you have the latest patches? Yes. 802.1x allows us to authenticate before we can get into the network. Not just on the system, but we authenticate to some server on the back end that says, oh, okay, yeah, you do have an account here. You can go ahead and get on the network as well. So multiple layers again, defense in depth to keep those vulnerabilities at bay. Now, another mobile device security concern, and probably a pretty big one, is loss or theft of the mobile device. Now, as soon as that happens, that takes away confidentiality, integrity, takes away availability. You obviously don't have it available to you if somebody has stolen it or if you've lost it. You don't have it with you. That also compromises the data that is on that particular device. Not only did you lose some hardware that may or may not belong to you, it may belong to a company, the data that was present on there is now gone as well. Now, backups assure availability and integrity of the mobile data, but your data is only good as your last backup. So if it was stolen on Tuesday and you did a backup on Monday, you may be okay. But if it was stolen on Tuesday and you didn't do a backup until last Wednesday, you've lost almost a week's worth of data. Now, it depends on how much data you go through, and it's going to be up to you on how much data you actually lost. But that may be a problem for most users. So, full disk encryption may help us with this. That could be used to ensure the confidentiality of the data on that laptop that got taken out of the building. Or you left it at the coffee shop and you got up to get some sugar and all of a sudden it's gone now. Somebody's out the door with it quick. Remote wiping capabilities is a very critical control when it comes to mobile devices. So what is remote wipe? Well, if somebody grabs my cell phone, I have the capability to get online, go to a certain provider, and I can track the phone and I can wipe the phone if it's stolen or if it's lost. Now, there are things that malicious users can do if they swipe my cell phone. Hopefully I have a screen lock on. Hopefully I have some type of passcode on there, and they can't just turn it on and start getting my data. If they can, if the screen hasn't locked yet. All right, some people set the screen lock to a very high number, 20 minutes, 30 minutes, an hour. What that means is if they unlock their phone by putting in the PIN or the pattern or your fingerprint or finger scan, if it's unlocked and you set it down, the screen may be off, but in the background it's still unlocked. If I pick it up and push the power button, all I gotta do is usually just swipe my finger to, swipe it over one way or the other to get into the phone. Well, now I can get your data. Well, the first thing I'm probably gonna do if I stole your phone and I can get that far is I'm gonna turn off the cellular signal. So you can't do a remote wipe and you can't track it. If you can't communicate with that device, then you can't do any of those things. That's where we need to rely on encryption for those mobile devices. What about embedded devices? Vulnerabilities in embedded devices. Now, these devices, these embedded devices, are small form factors. They're not super powerful, but they need to run some type of watered down operating system. They're meant to usually run maybe specific tasks, and they're not necessarily full-blown systems like your desktop and your laptop. We take this and we embed it in chips, but there's not necessarily a full-blown keyboard or anything like that. It's meant to do something particular, like your wireless router. It may have a embedded operating system in there, a watered down, proprietary possibly operating system, because it does certain things. Wireless routers, they route. It doesn't necessarily do calculations. I can't write a Word document on there or do a spreadsheet. It's meant to do what it's supposed to do. Your mobile devices, cell phones and tablets. Now, stop screaming. I know tablets can get pretty powerful nowadays. Microsoft touts they got the laptop replacement that is a mobile tablet device. And it is a full-blown operating system for all intents and purposes. Not exactly what we're talking about, so maybe I shouldn't even put that on there, but they do specific things. All right, now you can get more applications and put more stuff on there and more stuff on there, but they're still not quite as powerful as, say, a desktop or a laptop. Your media players, they have watered down operating systems, proprietary more than likely, because they do certain things. All right, super popular one now, right? The iPod. I say now, it's been popular for years and years and years. But it's a operating system on there. It's proprietary, and it does what it's supposed to do. Play music. Sometimes they can play whole pictures and videos, and may have a built-in radio now or whatever, and track your steps. And I mean, they're getting better and more powerful. But as all intents and purposes, they are embedded devices. You could have embedded devices in your vehicles that monitor tire pressure, monitor the engine, all right, the electrical systems in your car. That's all it does. You can't get in and do a spreadsheet on there or surf the web. Well, it's a different computer, but you may be able to surf the web if you tether your phone and all that, right? We'll be changing this course in 2 weeks because a new technology is going to come out and I'm going to be wrong. So I'll stop right there when it comes to embedded devices, but they are small, small form factors, what they're for, usually for specific purposes. So coming up, we'll continue with Domain 3, and we're going to talk about cryptography.